Hey, we're going to look at improper integrals. Now, what makes integrals improper is when you have some kind of an issue with the integral itself. And when we work through these things, we're going to have to be thinking about how to evaluate some of these types of integrals. And the real important part is all the details. So, an improper integral. This happens when it's not defined at one of the bounds. So this typically means that when you plug in, there are always definite integrals for improper integrals. You always have limits of integration. And there's something wrong with those limits. So if I plug in one of the endpoints, I get like division by 0, it's not defined. So that would make it improper. If one of the limits of integration was infinity or negative infinity, then I also have an improper integral because I can't plug in infinity. Or if the function is not continuous between the limits of integration. An example of that would be like you have an asymptote in the middle. Okay, so let's take a look at some examples. So the most common type you're going to come across are ones that you have an integral that's going off to infinity. These are particularly important because later you're going to look at sums where you'll go from like n equals 1 to infinity of 1 over n squared. And you have to decide whether this will have an answer or it diverges. That's what the goals are. So in order to do this kind of a problem, we do it using integral. That's how we actually go to figure this out. So this is one of the big topics that you actually use in calculus is the idea of series. So this is one of the reasons why we have to know how to work with this. Now I just can't plug in infinity. So because of that, I have to use limits to be able to make this into a proper integral that I can evaluate. So usually when we have an integral, it goes from a to b. Since my weird step is on the b part of it, I just labeled it as b. Now you can use any letter you want, just can't use x, because that's my integral variable that I'm using, so I can use anything I want. But I'm going to use the limit as b goes to infinity, so this was the upper limit, of the integral from 1 to b of 1 over x squared dx. Well, the antiderivative of 1 over x squared, I rewrite this as x to the negative 2. Then if I do the antiderivative, I add 1 to the exponent, I get x to the negative 1 divided by negative 1, which is negative 1 over x. Now I'm carrying my limit the whole time through, but now I'm ready to actually evaluate it. So I got the limit as b goes to infinity of negative 1 over b minus, when I plug in 1, I get negative 1 over 1. So as b goes to infinity, as this gets bigger and bigger and bigger, this fraction gets smaller and smaller and smaller. So this fraction right here, as b goes to infinity, will go to 0. Then I got minus negative 1, that equals 1. So that is what the area is under this curve. Okay, another example. This one is important because it has parts of it are graphs that you want to be able to recognize. This one is actually kind of a good graph to be aware of. So this graph is kind of a bell-shaped curve. It has the x-axis and asymptote. And what we're trying to do is find the area going from 0 out to infinity. So I'm looking for that area. Well, again, I have this issue of infinity. So I'm going to rewrite it as the limit as b goes to infinity of the integral going from 0 to b of 1 over x squared plus 1. Hopefully you recognize the antiderivative of 1 over x squared plus 1 is tangent inverse of x. So now I've got the limit as b goes to infinity of tangent inverse going from 0 to b gives me the limit as b goes to infinity of tangent inverse of b minus tangent inverse of 0. So remember, tangent inverse, I'm trying to find the angle whose tangent is. So the angle whose tangent equals 0 is 0. But this one, I'm looking for the angle whose tangent equals infinity. So now I've got to think about what that means. Remember, tangent is sine over cosine. So it's sine of x over cosine of x. So as cosine goes towards 0, when this denominator approaches 0, the angle is headed towards, I want to find out what angle will cause the cosine to go towards 0, making this result equal infinity. Now tangent inverse, if we look at its graph, looks like this. And when we use the unit circle, tangent inverse is defined from here to there. And you have to be aware of what those values are. So it's going to give us two asymptotes. So this is a graph that you want to be aware of. This is a graph of tangent inverse. And as tangent inverse heads towards infinity, which means cosine was going towards 0, well, cosine equals 0 at pi over 2. So the upper part of this was pi over 2. That's this asymptote. On the other end, well, if we were going to negative infinity, this asymptote right here happens at negative pi over 2. And that also corresponds with the bottom of my unit circle. So this one has two horizontal asymptotes. Always great to recognize this. So as b goes to infinity, tangent inverse as b goes to infinity is going to head towards pi over 2. So this answer is pi over 2. So I have seen this kind of a problem come up on the AP exam, so it's an important one to be aware of. Now you might start thinking, well, do these things always get an answer? So the function, if it's decreasing, does it, well, then will it always converge? We always get a number answer. Let's take a look at this example. So I have got the integral of 1 over x going from 1 to infinity. Well, antiderivative is ln of x. Now I didn't put absolute value on it because I'm going from 1 to infinity, so I know x is always greater than 0. So if you know that, you don't necessarily have to put the absolute value in it. So we have the limit as b goes to infinity of ln of b minus ln of 1. Well, natural log of 1, this is equal to 0. But as b goes to infinity, natural log of infinity, well, natural log keeps growing. It keeps growing and growing and growing. It doesn't grow very fast, but this right here will go to infinity. So we say this diverges. It diverges to infinity. Now, the big part is recognizing it diverges. If you wanted to specify the direction, then you could say it diverges to infinity. So this is the graph of 1 over x. And it's kind of interesting to think that this area right here, as you go out to infinity, is infinite. And we're going to discover that that particular function, the 1 over x, ends up being very important in calculus, particularly with series. Okay, let's take a look at some other types. These ones are not going to infinity, but they have issues at the endpoints. If I plug negative 2 into that equation, I'm going to be dividing by 0. So being aware of this, I need to rewrite it. Now when you have numerical endpoints, not infinity, we have to specify the direction they're coming from. So it's a lower limit, so I'm going to label this one as A. And the lower limit, the only way to get to the lower limit is from above. So anytime you're using a number and you're coming towards it, if it's a lower limit, you come from above. If it's the upper limit, you'll come from below. You use a negative. Well, the antiderivative of 1 over x plus 2 is ln of absolute value of x plus 2. And I'm going to go from a to 3. So if I plug in 3, I get natural log of 5. And since a is bigger than negative 2, because it's coming from above, I always know that's positive, so I drop the absolute value again. So natural log of a plus 2 as a approaches negative 2. Well, we need to figure out what this part is. This is the thinking part. So this is where you have to know what your graphs look like. So here's the graph of ln of x. ln of x plus 2, well, I'm just going to shift it to the left 2 points. This is the graph of ln of x plus 2. As x approaches negative 2 coming from above, this is headed towards negative infinity. So I end up getting ln of 5 minus, it's going to negative infinity. So it's going to diverge. It diverges to infinity, but it's okay to simply say it diverges. Okay, let's look at a harder case. And these ones you probably want to come across, but you need to be aware of. This has an asymptote in the middle. So what happens is I'm going from negative 1 to 1, and I have to look at the equation and say, oh, is there anything weird happening in it? And these are the ones that are really easy to miss. So if x equals 0, I'm dividing by 0. So I've got to break it into 2 pieces. So since I want to go to 0, I'll start from negative 1, going to 0, and then from 0 to 1. But since I can't plug in 0, I'll go from negative 1 to b, coming from below, and then I'll go from 0 to 1, but as a approaches 0 from above on this other one. So remember, anytime you use this upper limit, which is a number, we're coming from below. Anytime you use the lower limit, and it's a number, not infinity, we're coming from above. Okay, antiderivative will be the same on both these. We have x to the negative 4/5, so I add 1 to negative 4/5, I get 1/5, divided by 1/5 will give me 5. So I have 5x to the 1/5 for both my antiderivatives. Now I'm going to evaluate it going from negative 1 to b, and then from a to 1. So when I plug in b in this, I get 5b to the 1/5 minus 5 negative 1 to the 1/5. And then when I do the other one, I'll get 5 1 to the 1/5 minus 5a to the 1/5. Now as b goes to 0, 0 to the 1/5, well, the 5th root of 0 is just 0. So that becomes 0. Negative 1 to the 1/5, the 5th root of negative 1 is negative 1. So this equals negative 5 times negative 1, which is positive 5. This one, 1 to the 1/5 is just 1. 0 to the 1/5 is 0. So I end up getting 5 plus 5 equals 10. Now, some people sometimes will notice, well, what if I just didn't bother with the limits? I'll get that same answer. Yeah, but that's really dangerous, and I'm going to show you why. So let's take a look. And I did the integral going from negative 1 to 1, and you weren't paying attention, didn't really aware of what's happening in this, and you just tried to do the antiderivative. Well, the antiderivative of 1 over x squared is negative 1 over x. I'm going to evaluate it from negative 1 to 1, and I get negative 1 minus negative 1 over negative 1, so I get negative 1 minus 1. I got negative 2. And you might say, okay, that's fine, I'm all good. Well, let's see if we do it the correct way. So again, I'm going to go from negative 1 to 0, and then from 0 to 1. So I'll go negative 1 to b, and then I'll go from a to 1 for the second integral. Okay, antiderivative is still going to be negative 1 over x. Now I'm going to plug in b, and I'll plug in negative 1 for the first one. I'll plug in 1 and a for the second one. So I have negative 1 over b minus negative 1 over negative 1, so it's minus 1. Then I got negative 1 minus negative 1 over a. So as b approaches 0, we know I'm dividing by, as I divide by a smaller number, that's going to make this one bigger. Let's just take a look at the graph of -1 over x. I'm looking at the graph of what the antiderivative was. So here's a graph of -1 over x. As I approach 0 from below, I'm headed towards infinity. So this whole thing right here is equal to infinity. Then it's -1. Then I got -1 minus, as I go over here, as I approach 0 coming from above, this part is headed towards negative infinity. So I got infinity -1 and -1 plus infinity. This goes to infinity. So it doesn't equal -2. It actually diverges to infinity. Now, if you're aware of your graphs and you think first, you could possibly realize that this one, in fact, can't be -2. If I notice, x squared will always be positive. It'll be greater than or equal to 0. If I look at this graph, it looks like this. There's no way the area under this curve can be negative. The area we have that's infinite is this area that's in between, right in here. That area, all this area right here, going from -1 to 1, this area all inside is going to be infinite. Okay, let's look at one last example. Okay, so this one is improper because it has, when I plug in the 2, I'll be dividing by 0. So again, lower limit, I'll just call this a. So limit as a approaches 2 from above, the integral going from a to 6. This I'm going to rewrite as x minus 2 raised to -1/2. Now I can do my antiderivative. Add 1 to my exponent, I get x minus 2 to the 1/2, divide it by 1/2, or multiply by 2. Then I'm evaluating it going from a to 6. If I plug in 6, I get 2 times the square root of 4, minus when I plug in 2, I get 0. So I get 2 times the square root of 4. My answer is 4. Okay, so you guys have several problems you'll be working with. I'm going to show a couple review problems also that are kind of optional. So just in case you wanted to see some extra examples. So these are some new SIG test topics that will be coming down. So these are good examples, and have you guys have a couple questions to think about them, and then we'll come back to them. Okay, so now let's take a look at going through these answers. So a squirrel runs along a fence, so its velocity is found by, we have our equation, where v is measured in feet per second, t is measured in seconds. Always be aware of your units when you work through the problem. At t equals 0, the squirrel was 5 feet behind the center post. So that means my initial position is at -5. I want to know what was the average velocity of the squirrel. Okay, so be aware always of what you have. They gave us the velocity. I want to find the average velocity. That's the average of this function. That's the one we use the integral for. So it's the integral of v of t on the interval going from 0 to 2, and I divide by the width, which is 1/2. We evaluate it, and we end up with -2 feet per second. The units, when I do the average of the function, are the same as the original function. At t equals 2 seconds, is the squirrel running towards the center post or away from it? We've got to justify our answer. Well, I want to go over and need to know its position and its velocity. So to find its position, I'm going to use the fundamental theorem of calculus. I know its position at t equals 0. I need to know what its position is at t equals 2. So we evaluate this integral. It's going to be -6. I have my position 2 minus -5. So my initial position is -11. Now I need to know its velocity. So I need to know where it is and where it's headed. If I plug in 2 into my velocity equation, I get -3. So my position is negative, and my velocity is negative. So therefore, I am moving away since velocity and position are the same sign. Now I want to know if the squirrel is speeding up or slowing down. So on this one, I need to know what its velocity is and its acceleration. So I need to know if its velocity is positive or negative, and I got to see, is the acceleration the same sign or different sign? If they're the same sign, I'm speeding up. If they're opposite signs, I'm slowing down. So that's the key here. So velocity at 2, we already figured out. My velocity at 2 was equal to -3 feet per second. My acceleration is going to be the derivative of the velocity. And when I plug that in, I got +4. Since velocity and acceleration are different signs, I'm slowing down. Okay, one more example of some SIG test questions. So little reminders of integration by substitution. Why don't you try these first, and then we'll come back to it. Okay, so let's take a look at the first one. We have a straight substitution problem right here. If I let u equal x squared plus 1, when I take its derivative, I'm going to get an x. And that's kind of the clue that you're using. I'm looking for the derivative inside the integral. So u equals x squared plus 1, du is equal to 2x dx. Therefore, now if you need to take an extra step, I'm going to write that extra step right over here. I'll put it up here just because I won't run into my work. We would have the integral of 3x over the square root of u. I need to solve for dx. That's going to give me du over 2x. So I've got du over 2x. X's will cancel. And I got 3/2 times the integral of 1 over the square root of u. Now do those steps if you have trouble with doing some substitution and making sure you're doing the correct substitution. So it's always a safe way of doing it. A lot of you can do this part in your head, and after time you get better at doing it. So 1 over square root of u is u to the negative 1/2. Antiderivative, add 1 to the exponent, I get u to the 1/2. Divided by 1/2 is the same as multiplying by 2. Then that gives me 3 times the square root of u, and u was equal to x squared plus 1. So I get 3 times the square root of x squared plus 1 and plus c. Okay, this other one, this is the one you just recently learned. This you need to recognize is a form of sine inverse. Now in order to use sine inverse, I need to make that 4 into a 1. So I'm going to factor out the 3, and I'm going to factor out the square root of 4. So 3 over the square root of 4 would be 3/2. Then when I factor out the 4, I'm going to make this x squared over 4. I'll be able to rewrite this as x over 2 squared. Now I'm going to take the antiderivative. You could do substitution, but you don't need to in this one. If the term you're substituting for, like my temptation would be to substitute for the x over 2. If it's linear, you don't need to substitute. You can do it in your head. You just got to compensate for chain rule. So I have sine inverse of x over 2, but I have to compensate. So sine inverse of x over 2. So compensating for chain rule, if I took the derivative, I'd have times 1/2, so I got to compensate, so I multiply by 2. And that gives me my final answer.